order to facilitate our discussion of basic theory, we'll introduce some operator notation. So we will let L, the differential operator L acting on Y, is defined by the d to the power n, or the nth derivative of, plus p1 dn to the power n minus 1 plus dot 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 plus p sub n, all of this acting on y. And the standard form can then be rewritten as L acting on y equals g. It is essential to keep in mind that L is a linear operator. So when L acts on a sum, that's the sum of the operators. So this is L acting on y1 plus L acting on the function y2 plus dot 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 plus L acting on y sub m. Also, if we have a constant multiple times a function, then we can pull that constant multiple outside. So this is c times L acting on y. As a consequence, if y1 through y sub m are solutions to the homogeneous equation L acting on y equals 0, then any linear combinations of these functions, c1 y1 plus c2 y2 up to c sub m y sub m, is also a solution. So you can see that because when you take the linear differential operator of this sum, we can rewrite this as c1 times the operator acting on y1 plus c2 times the operator acting on y2 plus all the way up to cm times the operator acting on y sub m. And what we see here is that since we assume that y1 through ym are solutions, this is 0, this is 0, this is 0, and so the final answer is 0. Now, suppose that we have found n solutions, y sub 1 through y sub n, to our homogeneous differential equation. Is it true then that any solution to the homogeneous equation can be represented by c1 times y1 plus c2 times y2 up to cn times yn? To answer that question, we will use the following definition of Wronskian. So if f1 through fn are n functions that are each n minus 1 times differentiable, then the function, the Wronskian of f1 through fn of x, is given by the determinant, where the first row of the determinant is given by f1 of x, f2 of x, up to fn of x. The second row is given by f1 prime of x, f2 prime of x, all the way up to fn prime of x, and so forth until we reach the nth row of this determinant, which is given by f1, the n minus first derivative of f1 of x, plus the n minus first derivative of f2 of x, up to the n minus first derivative of fn of x. This determinant is called the Wronskian of the functions f1 through fn. On exams, the largest determinant you will have to find is a 3 by 3 determinant. So in order to find a 3 by 3 determinant, we're going to look at the first row of the determinant, and then we're going to take a look at the cofactor of each of the terms in the first row. So for A, the cofactor is A times the minor determinant EF H I. And then for B, the cofactor is minus B times the determinant DFG or DFGI. And then for C, the cofactor is plus C times the minor determinant DEGH that we see over here. And now for the determinant for a 2 by 2 matrix, what we do is we multiply these diagonal elements, and then we multiply these elements here and subtract that from each other. So this is A times EI minus FH, and then minus B times DI minus FG, and then plus C times DH minus EG. Another trick to calculate a 3 by 3 determinant is by copying the first two columns. So we see we have the determinant of A, B, C, D, E, F, G, H, I. And what I did here is I copied the first column, A, D, G, next to the determinant, and then the second column, B, E, H. And now what I can do is I can look at the diagonal products. So first, let's take a look at A, E, I. So we have A, E, I. And then the second diagonal product is B, F, G. So I'm going to add B, F, G. And then the third diagonal here is C, D, H. I'm going to add C, D, H here. And I'm going to do the same thing, but now with the opposite diagonals. So I have C, E, G. I'm going to subtract that, minus C, E, G. And then A, F, H. So minus A, F, H. And then finally, the last diagonal is B, D, I. And you should verify for yourself that when you write this out, you get this expression right here. I'll quickly take a look at two terms, A, E, I. That's what you see here. And then minus A, F, H. That term is what you see here. But you should verify the other terms as well.